So hello, this is the PMRF. This is the NPTEL Algebra 1 course, and I am one of the PMRF TS. I am Shubhajit Das, and welcome to week 5. So as we keep on doing every week, we solve problems based on previous year assignments, and I hope you have had attended Harish's session yesterday. So he solved some problems, and I'll be solving the rest of them. Okay, so let's start. So let us start with the first problem. So this week you have covered presentations of groups. You have talked about, you have studied free groups. So the questions will be based on all of that. Okay. So let's read out the first problem. So you are basically given the presentation of some group G, and the presentation is as follows: that the generators of the group are A, B, C and D, and you have 4 relations as given here. So AB is C, B times C is D, CD is A and DA is B. So you are asked to find the order of the group G. Okay. So the first thing that we need to do is, we are given a set of relations, but we sort of need to find out what do these relations imply in particular. Okay. So let us sort of unravel the given relations to obtain something more fruitful, which would be useful to us. So first of all, let us write down the given relations. So given relations AB is equal to C, BC is equal to D, CD is equal to A, and DA is equal to B, right? So we see that if we take the relation AB is equal to C, and if we multiply D on both sides, so this will imply ABD is equal to CD, and notice that the third relation, so this is the first relation, this is the second one, this is the third one, and this is the fourth one. So notice that the third relation implies that CD is A, from which we get that BD is equal to the identity element of G. So this further implies therefore that B and D are inverses of each other. Similarly, if we take the relation BC is equal to D, and if we multiply both sides by, let's say, A, so this implies BCA is equal to DA, and notice that the fourth relation implies that this is B. So from which, applying a cancellation again, we get CA is equal to E, which therefore gives you A is equal to the inverse of C. Okay. So once we have this, so we know that A and C are mutual inverses, B and D are mutual inverses. Now let's try to see if we can find out some relation between A and B. Indeed we can, because again if we use the first relation, AB is equal to C, then this implies that so AB is equal to A inverse, since C is A inverse as we have found out. So this implies that B is A to the power minus 2, and hence we also have D, which is B inverse, which is therefore equal to A square, right? So we have basically found out this, that we are given a set of 4 generators, and we indeed see that every other generator, every generator is a power of A, right? So this suggests that the group should, it should be generated by a single element, which we are considering to be A here. Okay, but still we don't have much information about the order of the group. So now let us try to at least comment something on the order of A, right? So now we also have this relation, right? Which one? Let's say, so we have B is A minus 2, C is A inverse, and D. Yeah, so let us use, now using relation 2, we have BC is equal to D, which implies that A power minus 2 times A inverse, since C is A inverse, is D, which is A square, right? So we have A power minus 3 is A square, from which we get that A to the power 5 is 1. So this is something really important now. We have obtained that A to the power 5 is 1, right? Which means that the order of A is either 1 or it is 5. We are still not sure what it will be, but we know it's either 1 or it's 5, because order of A has to divide 5, right? Okay, so let me write, instead of 1, let me write E, the identity of the group, right? Okay, so the order of A is either 1 or 5, we still don't know. So the point is, we at least have some information that the group must have order less than equal to 5, right? It can be Z5 or it can be the trivial group, right? So let's try to use the universal property of free groups. So let me make some space here. Let's say okay, so let us now try to use the universal property of free groups, the so-called universal property. So I hope that you have learned about the universal property, and we have used it the last week as well. So let us just use it, try to use it. So first of all, let us see whether we have some, whether, I mean, the plausible groups here are either the identity group or Z5. So let us see that whether we can find elements in Z5 which satisfy the same relations as A, B, C and D. Okay, so what we do is consider this mapping. So we consider the mapping of the set A, B, C, D, which is in the group G, right, into Z5. This is just a set map. What we are doing is we are mapping A onto 1, B onto 3, C onto 4 and D onto 2. Let's see whether A, B, C, D indeed satisfy, I mean, let us see whether the images of A, B, C and D indeed satisfy these relations. Okay, so keep in mind that even though we have written the group G using multiplicative notation, the operation is addition for Z5. Okay, so AB, let us see whether AB is C, right? So indeed, I mean 1 plus 3 is certainly 4, right? So we have this, whether B times C is D, right? Which means that 3 plus 4 has to be 2, right? And 3 plus 4 is certainly 7, which modulo 5 is 2. So the second relation is also satisfied. C times D is A, right? So 4 plus 1, which is 5, sorry, C times D. So 4 plus 2, which is 6, right? It's 6 is certainly 1 mod 5, right? So this also holds. And D times A is given to be B, right? So D times A is 2 times 1, right? So 2 times 1 is sorry, not 2 times 1, 2 plus 1, D plus A, which is 2 plus 1, which is 3, right? Which is certainly B. So we see that since, okay, so whatever, not this, so first of all, this is a set mapping of ABCD into Z5, right? And we know using the universal property of free groups, we know that free groups are very special kinds of groups, right? They are determined or characterized by some universal property. So using the universal property of free groups, we know what is a universal property of a free group generated by a set X. So you take a set X, it has you have already have a map X2, from X to the free group generated by X. Let's call it F, right? And this map is universal among all such maps, right? Which means that given any set map from X to any group G, this particular new map from X to G will actually factor through the map from X to F, right? Which means that, in other words, what this means is that uh, the map from X to G can be extended uniquely. It has to factor uniquely. So it can be extended uniquely to a map from Fx to G, right? Yeah. So using the universal property of free groups, there exists a unique group map or a group homomorphism from the free group generated, let's denote it like this, free group generated by the set ABCD into Z5. We get a group homomorphism of this into Z5. Okay. Now, notice something interesting here, that this clearly extends ABCD, right? That we know. And notice something here, that since 1 generates, so by 1 I actually mean class of 1, okay? Since 1 generates Z5 and 1 is in the image, so let's call this group homomorphism to be phi, let's say. It's in the image of phi, hence phi is surjective, that we clearly know, right? Because any element of Z5 is some combinations of 1, it's some compositions of 1, right? And you can take A in the free group, and you can consider the same the same composition of that many A's, right? And that will be mapped onto this given element of Z5 via phi, right? So clearly phi is surjective. Also, since phi of A, which is 1 basically, so there is, okay, so let me write something extra here. Using the universal property of free groups, there is a unique group homomorphism from this to this, which extends the set map from ABCD to Z5, right? So since phi A, phi B, phi C, phi D satisfy the relations, we have already checked this. The phi A is 1, phi B is 3, phi C is 4, and phi D is 2. Since they satisfy the relations of G, right? Hence, what this basically means is that phi factors through the map so let me add some space. So certainly phi factors through the through the quotient modulo the relations A, B, C inverse, B, C, D inverse, right? And what else is there? C, D, A inverse, D, A, B inverse. Phi factors to this quotient, and this quotient is precisely your given group G, right? That is the definition of the presentation of a group, right? So let me write it. So this is just the group with presentation A, B, C, D, says that ABC inverse is identity, that is AB is C, BC D inverse is identity, BC is D, and CD is A, and DA is equal to B, right? Right, which is precisely your given group G, right? As follows. So it factors as follows. So we get a commutative diagram, right? So it's like, it's this. So you have if A, B, C, D, right, which is your given free group. You have a map into Z onto Z5, and here you have G. So here you have the projection map, and here you have a map. So this is phi. Let's call this psi, right? And this is just the projection, right? So this is the canonical projection map, right? Now the point is, since phi is surjective, hence psi is surjective, right? That's a simple set theoretic statement, very simple to check. Indeed, if psi cannot reach all elements, cannot map onto all elements of Z5, phi won't be able to do, right? Because phi is psi composed with the projection, right? So psi comes after the projection, right? So since phi is surjective, psi is surjective. So what we have here is, we have a surjective group homomorphism from G onto Z5, right? Hence, we know that the cardinality of our group G has to be greater than equal to 5, right? But we also saw, since every element in G, in particular the generators, A, B, C and D is a power of A, right? Is a power of A, and A to the power 5 is identity in G. Hence, cardinality of G has to be less than equal to 5 as well, right? So we get that the cardinality of G is greater than equal to 5 and it is less than equal to 5. So what is your only option, right? What is the only thing that you can say from this? So let me add some more space. So the only conclusion that we can draw is, hence the cardinality of G has to be 5, right? And we know what is the only group. I mean, we don't even need that here, because since cardinality of Z5 is equal to 5 and psi mapping G into Z5 is surjective, we clearly know by the pigeonhole principle that hence psi is bijective, right? It's an isomorphism, therefore. Thus, psi is an isomorphism of G onto Z5, right? Hence, G is isomorphic to Z5, and we are done. So the group finally turns out to be Z5. This given group is actually Z5. Okay, so let's move on. let's turn to our next problem, which is question 2, right? Again we are given some group G and we are given a particular presentation of our group G. Okay, so we need to find out what concrete group this is, right? So again we have to work with this given relations. Okay, so again we write down the given relations. So given relations, x is equal to xy cube and y is equal to xy power 4, right? So we see that hence x so from this we see that hence we see that if we multiply xy with x, this is just xy cube times xy, which is xy power 4, right, which is y, which therefore implies that x square y is equal to y, and therefore by right cancellation you get x square is equal to identity, right? So we have one more relation, x square is identity. Again so yeah, so if we now take y x inverse, so if we take y x inverse, okay, so if we just take yx, we know that x square is identity, which means that x is its own inverse, it's self invertible. So yx can be written as yx inverse as well, but yx inverse is just, if we take the value of y, I mean take the second relation xy, y is just xy power 4 times x inverse times x inverse, which is xy power minus 3, right? And this turns out to be xy, right? So the point is that x and y commute, right? This is what is given here. So the point is that x and y commute, so y is yx, right? So indeed that in particular implies that the group has to be abelian, since xy generates the group, so every element is some finite word in G. So certainly and if the generators x and y commute, so certainly the group has to be abelian, right? So we have one more relation. So x square is identity, xy is yx. Now we know that x, from the first relation, x is given to be xy whole cube, right? This is xy, xy, xy. But since x and y commute, this is just x cube, y cube, right? As x and y commute. So, and that therefore implies, if you now just use left cancellation by x inverse, so you get identity is equal to x square y cube, but we already know that x square is identity, so this is just y cube, right? Hence we have three relations. Okay, hence we have x square equal to e, y cube equal to e, and the group, and xy commute, x and y commute, so that is xy is yx, right? So certainly the group for sure has to be abelian, which means that option C is not correct, right? But we still don't know whether it will be option A or option B or option D, right? But since we already have an element which satisfies x square is identity and an element which satisfies y cube is identity, we still don't know whether x is identity or y is identity. But since at present we don't have any other relations at hand, right? That means we only have x square is identity and y cube is identity. So it's very plausible that the group that we are looking for can be Z6, right? So let's again use the same trick that we did, that is we are going to use the universal property of the free group, right? So what we do here is again consider the set map. So consider the set map xy from xy into Z6. So we take a mapping of xy into Z6. Okay, and what is this mapping precisely? So given by x, notice that x square has to be identity, right? So we know that some element in Z6 which when sort of added to itself once gives you 0, right? That is 3. So we map x onto 3, and y, we are mapping y onto y cube is identity, so we need some element which when added to itself 3 times gives you 0, right? So we take 2, right? Now notice that the images of x and y under this mapping again satisfy the same relations as x and y, right? So you can check this, that as we did previously, that 3 is 3 plus 2 whole cube. I mean, just keep in mind that the operation in Z6 is addition. So we have 3 is equal to 3 plus 2 added to itself 3 times, right? 3 into 3 plus 2, right? So yeah, I should write class of 3 and class of 2 here. So yeah, so class of 3 is equal to 3 times class of 3 plus class of 2, right? This is certainly true in Z6, right? Because it's class of 5, and what you are doing is you are multiplying by 3, so you get 15, and it's just 3 mod 6, right? So this first relation holds, and the second one also holds, right? And class of 2 is also equal to, so you have to have y is equal to xy power 4, right? So class of 2 has to be 4 times class of 3 plus class of 2, but that again clearly is true, right? Because you are taking 5 times 4, which is 20, which is certainly 2 modulo 6, right? So this holds in Z6. So this holds, these two relations hold in Z6, okay? So now this is just a small observation that we are going to use just as we use in the first problem. So let me again make some space here. Anyways, can someone comment whether I'm audible and my screen is visible? Can someone comment in the chat maybe? Just need to make sure. Can someone please comment? So anyways, using the universal property of free groups, the above set map extends uniquely to a group map or a group homomorphism from the free group on the set xy into the group Z6, right? We get a unique homomorphism. Let's call this, let's say, sigma now, okay? So the above map certainly extends to a unique group homomorphism, and since sigma of x, which is your which is 3, and sigma of y, which is we have taken to be 2, right? The previous set map, which is extended to sigma. So since these two satisfy the same relations as that of G, as we checked, hence sigma factors through the projection, just as we have done in the problem. So sigma factors through the projection, or through the quotient map, let's say. It's better to write quotient map. Script f. So script f of x comma y onto script f of x comma y modulo the relations. So yeah. So xy whole cube x inverse and xy whole power 4 y inverse, right? These are your relations. So just let me make some space here. Okay, so this factors to this quotient map, but this second group, as we know, is just as we have defined the presentation of a group, right? Xy such that xy whole cube is equal to x and xy whole power 4 is equal to y, right? And this is just your group G, right? So the factoring is as follows. So we get a commutative triangle as before, x comma y z6. You have this projection G or this quotient map, and you get this map from G to Z6, right? So this is sigma, we are calling this tau, let's say, right? Now again we have the same thing going on here, just as we did it previously. So this triangle is commutative. Now since Z6 since let's say since the image of sigma contains the element sigma x, I have taken x to be 6, x to be 3 here, right? Sigma x minus sigma y, which is 3 minus 2, which is 1. And since 1 generates Z6, hence we have this, that sigma is surjective. And since sigma is surjective, and sigma is the composition tau composed with the quotient map, thus tau is also surjective, right? So we get a surjective homomorphism of G onto Z6, right? So we certainly know since G can actually cover Z6, so the cardinality of G has to be greater than equal to 6, right? It has to be at least 6. Yeah. So thus tau mapping G onto, so this is onto Z6, being a surjective map or a surjective homomorphism, gives that cardinality of G has to be greater than equal to 6. But then again, we know that every element of G is of the form x power I y power j. Notice that we have found out that that x square is identity, y cube is identity, and xy is yx. Now since G is generated by x and y, so every element of G is some finite word in x and y, right? But since again x and y commute, you can bring x's together and y together. You can separate them. So every element is a power of x. Every element is of the form x power I y power j, where I has to be between 1 and 0 and 1, and j has to be between 0 and 2, right? Because y cube is 3 and x square, y cube is identity and x square is identity, where 0 less than equal to I less than equal to 1 and 0 less than equal to j less than equal to 2, right? Thus we also have how many such elements are possible. So any element is of this form x power I y power j, right? And I can take two values 0 and 1 and j can take three values 0 and 2. So we know that g has at most 2 into 3, which is 6 elements, right? So g can have so g has at least 6 elements, and we also have g has at most 6 elements, right? So what is the only possibility? This means that g has exactly 6 elements. Right. Thus cardinality of g is is 6, and since cardinality of z6 is also 6, and as we saw here that tau is a surjective map from g onto z6, so again we know that using the elementary pigeonhole principle we get that tau is bijective, and tau maps g into z6. So tau maps g into z6 is surjective, hence tau is bijective. It has to be injective in particular. Hence tau is bijective. Thus tau mapping g into z6 is an isomorphism. Consequently, g is isomorphic to z6, right? And therefore the correct answer here is this. So z6 is the correct answer. So moving on, I hope you don't have any questions with this. If you have, in case you have, you can always ask me in the chat. So moving on, oops. Yeah, so moving on. So we are asked to find out whether this is true or false, this statement that this group G, which is of this form, which has this presentation, is actually isomorphic to Z6. But see, since we already were concerned with question 2, and in question 2 we are given a group G which has this two particular this particular presentation, right? That G is generated by x, y, and x, and these two relations hold. From these two relations we obtained that x square is identity, y cube is identity, and xy is yx, right? Now observe that we are given the same thing here, right? G is generated by x and y, and x square is identity, y cube is identity, and xy is yx, right? So it's very plausible that it will be isomorphic to z6. I mean, there's not much to check here, because because right after we showed that these three relations hold for the previous group, we never use the other two relations, right? That is the original two relations, right? X is xy whole cube and y is xy whole to the power 4. We didn't use these relations, right? So that is why I mean, after that whenever we are computing, we didn't use these relations. So it's we only use these three relations: x square is identity, y cube is identity, and x and y commute. So it's natural to say that G is isomorphic to Z6, but let me again give you a sketch of the argument. Okay, so this is the solution is same as above. Okay, so this is just a small sketch. I mean, we have already done this, but let's just use. So we mention the relevant steps, right? So take the mapping of xy into z6. This is a set map which maps x onto 3 and y onto 2, right? Yeah. So this extends to a surjective map. This extends uniquely to a surjection or surjective homomorphism, that is an epimorphism, of the free group on two letters onto Z6, right? So we are basically doing the same thing. You are taking the set xy and you are taking Z6 as a set, and you are considering a mapping of xy into Z6, and right after that what you are doing is you are extending it uniquely to a surjective homomorphism of the free group generated by x and y onto Z6. This will be a surjective map as we saw previously, precisely because one is in the image, right? So this will factor through the quotient map to G, right? G has that particular presentation as we saw previously as well. So if you just take the quotient by x square, y cube, and x, y, x inverse, y inverse, you just get G precisely, right? So this factors through this quotient, okay, and gives a homomorphism as before, rather a unique homomorphism from G to Z6, okay. And okay, so let me also write it as surjective, right? Since the original map from the free group to Z6 is surjective, and this is a factor which comes after the quotient map in the factorization of the previous surjective homomorphism. This map G to Z6 comes later, right? So I mean you have to apply the quotient map and then this map from G to Z6. So we get G to Z6 is also surjective. I mean, even though I'm saying it verbally, you can always check it mathematically. It's a basic set theoretic issue that can be dispensed of easily. So gives a surjective homomorphism from G onto Z6, right? Thus, we get cardinality of G is certainly greater than equal to 6. Again, okay, so we add this in step 4. Cardinality of G is less than equal to 6 as before, right? Every element is of the form x power I, y power j, where I is between, okay, so I maybe missed a certain thing here. I will be between, okay, x square is identity, right? Yeah, sorry. So that's correct. We didn't do anything wrong, right? Yeah, so the point is that every element of G is some x power, is of the form x power I, y power j, where I is between 0 and 1 and j is between 0 and 2, as done previously, as before. So cardinality of G is less than equal to 6. Thus combining 3 and 4, we get cardinality of G is equal to 6, and 5 therefore says that this map that we have from G into Z, in fact onto Z6, is therefore bijective, an isomorphism. So since we are using this map again and again, I mean G to Z6, that is why I didn't bother to name it, okay, but this is just the given map. I mean this is just the map surjective homomorphism that we have obtained in step 3, therefore an isomorphism. Hence G is isomorphic to Z6, and therefore this is true, right? This is not false, this statement is actually true. Okay, so let's come to the next question, and this is very easy. So you are asked to find out whether this statement is true or false, that is Q, the rationals under addition, whether this as a group is finitely generated or not. Okay, so let me ask you, there is only one person, I believe, Bhuvaneshwari, right? So what do you think, Q under addition is finitely generated or it isn't? Maybe if you, maybe you can comment in the chat as well. I claim that it can't be finitely generated, okay? That is, it will be false actually. So the point is, suppose that Q under addition is finitely generated, and let's say we pick some generators for this. So A1 by B1, A2 by B2, AN by BN is a generating set of Q under addition. Okay. Now the point is that B1, B2 up to Bn are all integers, right? We can take them to be positive. That doesn't matter because we can always take AIs to be negative, positive as we want. So BIs can be taken to be positive. The point is that they are either 1 or some positive integer greater than 1, right? And we know that by the fundamental theorem of arithmetic that every positive integer greater than 1 can be uniquely broken into a product of primes, right? So the factorizations of, okay, so let's write this in a more clever way. Okay, so the point is, by the fundamental theorem of arithmetic, there exists finitely many primes P such that P divides Bi for some I between 1 to n, right? Basically, you are taking factorizations of the denominators B1, B2, B3, B4 and so on, and B1 has finitely many prime factors, B2 has finitely many prime factors, up to Bn has finitely many prime factors, right? So if we collect all these factors together, the point is that there are only finitely many primes dividing some Bi, some denominator Bi, right? Since the number of primes is infinite, that is a very well established fact, right? Euclid's theorem or Euclid's lemma, I guess. Infinitude of primes. Since the number of primes is infinite, there exists a prime, let's say Q. Okay, there exists a prime Q such that Q doesn't divide any Bi, right? For all I from 1 to n. So we get some Q prime which doesn't divide, which divides none of the denominators. Then you can check easily that 1 over Q doesn't belong to the subgroup generated by A1 by B1 up to An by Bn, right? Precisely because what are the elements in the subgroup generated by A1 by B1 up to An by Bn, right? These are just additions of multiples of these elements Ai by Bi, right? And whatever you do, you can only add, right? You can add copies of Ai by Bi with themselves, right? So the point is you can never get some new prime in the denominator, right? You can only obtain primes which are present in Bi's, right? As denominators, right? So in particular 1 over Q cannot be in this, but 1 over Q is clearly a rational number, right? Hence the subgroup generated by A1 over B1 up to An over Bn is a proper subgroup, right? It's a proper subgroup of Q, right? So the subgroup generated by these AIs is Ai by Bi's is clearly a proper subgroup of Q, right? And hence this is a contradiction, right? Because we clearly assume that this finite set Ai by Bi as I goes from 1 to n generates Q, right? So the subgroup generated by it should be Q, but we clearly saw it's not Q. It's a proper subgroup of Q. So this is a contradiction. Hence, Q under addition cannot be finitely generated. It is infinitely generated. or rather we say it is not finitely generated. It can't be finitely generated. So this is clearly false, right? Q under addition is finitely generated. This is certainly false. And that finishes the proof. That finishes this question. So let us move on to the next one. So before we solve question 5, let us go to question 6 instead, because we will be using something from question 6 to solve question 5. Okay, so let's see the question first. So you are given that G is a group of order 8 which has exactly 5 elements of order 2. Then G is isomorphic to which of the following groups? That is what we need to find, right? So your first option is Z8. Your second option is Z2 direct sum, Z2 direct sum, Z2. C is Q8, which as you know is a quaternion group. And the fourth one is D4, which is the dihedral group consisting of 8 elements, right? That is, it is precisely the, as you know, it's the series, is a group of symmetries of the square, regular square. So first of all, we clearly can sort of reject two options from here, Z8 and Z2 direct sum, Z2 direct sum, Z2, right? So A is not correct, as Z8. What is Z8? It's the cyclic group of order 8, right? Now we know that every cyclic group consists of exactly one cyclic subgroup of order D, where D divides the order of the cyclic group. Every finite cyclic group of order n contains exactly one cyclic subgroup of order D, where D divides n, right? So if we are trying to find elements of order 2, we know elements of order 2 basically give rise to a subgroup of Z8, right, of order 2. And there is exactly one such subgroup of order 2 in Z8, right? So A is not correct, as Z8 has exactly one subgroup of order 2 and hence exactly one element of order 2, right? But we are given that G is a group of order 8 which has exactly 5 elements of order 2, right? So Z8 can't be correct because Z8 has exactly one element of order 2. So this sort of rejects option A. Let's look at Z2 direct sum, Z2 direct sum, Z2. Again, this is not correct, right? So B is not correct. Why? Simply because every element in this direct sum, Z2 direct sum, Z2 direct sum, Z2, every element here has order 2 except the identity element which is order 1, right? So every non-trivial element of this group Z2 direct sum, Z2 direct sum, Z2 has order 2. As every element of Z2 direct sum, Z2 direct sum, Z2, I should write non-trivial element, every non-trivial element has order 2, right? And why is this so? Because if you take any arbitrary element in this, let's say ABC, which is not identity, which means that at least one of A or B or C has to be non-zero, then this if you add two copies of it, you get 2A, 2B, 2C, which is 0, 0, 0, right? And hence it clearly has order 2. It cannot be 1 since we have taken it to be non-identity. So it clearly has order 2, right? Now how many non-trivial elements does this have? This group has 8 elements and you have exactly one identity element. So there are exactly precisely 7 elements of order 2. But as we have mentioned in the problem, that G must have exactly 5 elements of order 2. So this cannot be a correct answer. Again, let's look at Q8. So before I proceed, do you actually know what is a quaternion group Q8? Can you comment in the chat maybe? It's okay, you can just write down something in the chat so that I know that you understand what Q8 is. I am audible, right? And my screen is visible, right? Can you write down something in the chat? Excuse me, Bhuvaneshwari. Okay, so let me just write down what Q8 is. Q8 is this group 1 minus 1 I j k minus I minus j and minus k, right? And it has these relations where I, the 1 minus 1 when added gives you 0, I minus I gives you 0, and so on. You have ij is equal to k, the group operation, under the group operation. Jk is equal to I, and what else? Ijk, jki, and ki is equal to j. And you have I square is equal to j square equal to k square equal to minus 1. Indeed, Q8 has, you can check this, that Q8 actually has this presentation. So Q8 has this presentation. It is generated by A and B such that A square is B square, which is equal to AB square. The hint for this is to first show that A to the power 4 is identity, and then conclude. So first show that A to the power 4 is identity, comma B to the power 4 is identity, and conclude that Q8 has at most 8 elements. Precisely what we have been doing so far. So the point is, we know these relations, whatever Q8 consists of and so on. So we certainly know that since I square is equal to j square equal to k square equal to minus 1, we certainly know that I, j and k, and hence minus I, minus j and minus k, all have order 4, right? That is, you have to square once more to get 1, to arrive at 1. Now minus 1 square is certainly 1. This is, the way we have written, even though we haven't mentioned everything here, what are the exact compositions and all that, but it's clear from the notation that minus 1 square is 1, right? Indeed, minus 1 square is 1. We take this as one relation and all that. So the point is, Q8 has exactly one element, namely minus 1 of order 1, I mean order 2, right? This Q8 cannot be correct, is not a correct choice. Why? Because we have clearly mentioned that the group G that we are talking about has exactly 5 elements of order 2, right? So we are only left with one option, that is D4, right? The dihedral group with consisting of 8 elements. And indeed it is the right answer. And that's very easy to understand because you have covered D4 previously, right? So the elements of D4 are basically, so let me write down the presentation first. So this is A, B such that A to the power 4 is B square is equal to BA is equal to E, identity, right? So D4, the elements of D4 can be written in the form A square, A cube, and B, BA square, BA cube, as you have clearly seen previously, right? Now all these elements, these are just your reflections, right? So I wonder why I have to keep on adding so many spaces today. I'm writing too much, I think. Right? So these are all reflections they have order 2, and these four, I mean a square, a cube, all these are clearly rotations, right? But out of this has order 2. Since a to the power 4 is identity, a square has to have order 2, right? So and a cube are all of order 4. E has order 1, right? Thus D4 has exactly 5 elements of order 2. Thus D4 is the correct option. Answer. Right? Now notice that while we are solving this, so D4 is correct. So while we were solving this problem, we were basically dependent on the choices that were given to us, right? Z8, Z2 direction, Z2 direction, Z2, Q8, D4, right? But we could also do it in a much more rigorous way where we wouldn't need any choices, right? Basically the thing one would like to do is classify all groups of order 8, right? And then find out which group has exactly 5 elements of order 2. Now if the group is abelian, you can just use a structure. I don't know if you have studied the structure theorem or it was introduced to you as of yet, but once you study, maybe it will be clear what are all the abelian groups of order 8. And for the non-abelian case, you have Q8, D4, right? So I guess there is some other group which I am forgetting right now. So D dihedral group, Q8, and what is the other group of non-abelian group of order 8? Is there any other group? Maybe there is no other group, but anyways, the point is you will arrive at an answer, right, for this question. We could just directly could classify groups of order 8, and we could work out we could look at each and every particular group and try to see how many elements of order 2 does it actually have, right? Okay. So for this particular problem, the answer is D4. We sort of showed that the other options are incorrect and D4 is correct. So let's come to question 5 now, right? So again, you are given a group G. You can check that this is a group under multiplication. So we have just mentioned it directly that let G be this particular group consisting of all upper diagonal matrices which have exactly 1 in their main diagonal or leading diagonal, and the entries are from Z2, right? Which is the field consisting of 2 elements, which is just integers modulo 2 in other words, right? So we need to find out which of these groups is Z2 actually, is G actually isomorphic to. So the trick that we are going to use is precisely count the number of elements of order 2 in G, right? Okay. So first of all, let us understand the multiplication. So we understand the group operation. So you take 2 arbitrary group elements in G. So one is 1 0 0 A B 1 C 0 1, and you take another element 1 A prime B prime 0 1 C prime and 0 0 1, right? So if you take their product, this is just equal to 1. You can check that these are all zeros and ones and 1. So what you have for this element in the first row and second column is, so if you just multiply, so this is A prime plus A, okay, and the element in the first row and third column is, so you have B prime plus A C prime plus B, yes, A C prime plus B. And what you have for the, let me write it more spaciously, so 1 1 0, what you have here is just so you multiply the second row with the third column, right? So 0 C prime plus, yeah, C prime plus C, right? So notice that we have this is your group operation, and notice that the only thing that actually prevents this group from being abelian is this particular term, right? A C prime. This is what actually makes the group non-abelian, because if you just take the second matrix first and the first matrix second, and if you try to multiply, here you would actually arrive at A prime C. So AC prime and A prime C need not be the same thing, right? That is why the group is non-abelian. So let me sort of highlight this with a different color. Precisely because of this term, we have that this G is non-abelian. And we already can discard two options from here, Z8 and Z2 direction, Z2 direction, Z2, which are clearly not abelian. Okay. Now what we try to do is, let us try to find out the number of elements of order 2 in G. So if we can find out that the number of elements in the group G is 5, then we know that the group has to be isomorphic to Q8, sorry, D4, and if the number of elements of order 2 in G is 1, it has to be Q8, right? So let us find the number of elements of G of order 2. So if you just take 1 A, B, 0, 1, C, 0, 0, 1, and if you take it square, this is just according to our definition, according to the multiplication that we have. So this is A plus A, that is 2A. So 1, 0, 1, this is 2C, this is 2B plus AC, right? And since we are taking over Z2, so 2 times anything vanishes, right? So we have 1, 0, 0, 0, 1, 0, 1, 0, AC, right? So we basically observe that we just, for this to be the identity matrix, we just need AC is equal to 1. Thus, 1AB, 0, 1C, 0, 0, 1 square is identity if and only if AC is equal to 0, right? So now it's very easy to count the number of elements actually. Notice that B doesn't actually play a role in determining whether this particular element has order 2 or not. So B can be taken to be either 0 or 1. So if B is equal to 1, then there are 3 options, 3 such elements. Namely, the cases A equal to 0, C is equal to 0, or A is equal to 1, C is equal to 0, or A is equal to 0 and C is equal to 1, right? These are your 3 such elements. Notice that if we take B to be 1, then this matrix 1A, B, 0, 1, C, 0, 0, 1 is actually a non-identity element because B is 1. And you have these 3 cases. You can take both A and C to be 0, or you can take A to be 1, C to be 0, or you can take A to be 0 and C to be 1. What happens for the case B equal to 1, B equal to 0? If B equal to 0, then there are 2 choices. 2 such elements. So A equal to 0 and C is equal to 1, or A is equal to 1 and C is equal to 0. Notice that we discarded the case that both A and C are 0. Why? Because since B is equal to 0, if A and C are also 0, then we get the identity matrix, right? But the identity matrix actually doesn't have order 2, right? It has order 1. Even though it satisfies the fact that identity square is identity, it doesn't have order 2. It has order exactly 1. Right? That is why we need to discard the case that both A and C are 0 when B is 0, right? So thus there are 5 elements. There are exactly 5 elements. 5 elements in G of order 2. Hence, using problem 6, we understand or we know that the correct answer is, let me just add some space. The correct answer is certainly D4. D4 is the correct answer. Okay. So here again D4 is the correct answer, because Q8, as we saw, Q8 has exactly 1 element of order 2, right? So D4 is the correct answer. So that finishes question 5. I hope you don't have any questions, but if you have, you can always unmute yourself and ask. And we have also solved question 6. So we have question 7 now. Okay, so I have one other question. Let's see if we can do this today, or maybe I can just I'll just include the solution. Let's just solve question 7 and maybe then let's just end here. And the point is that this question is very easy, right? Simply if you understand what is the definition of the subgroup generated by a subset, you understand everything. So let G be a group and A and B be elements of G. Then you are asked to find out which of the following two statements are correct. So the first statement says that the subgroup generated by A and B is the same as the subgroup generated by A and AB. And the second says that subgroup generated by A and B is equal to the subgroup generated by B square and BA B cube, right? So let's deal with one first. So let's look at A. So what is the definition of this? So let's just write the definition of a subgroup. So recall, I'm sure you have done this in the class, in the NPTEL lectures, you have learned this. So recall that if G is a group, or let's use a different symbol. If K is a group and S is a subset of K, then the subgroup generated by S is the smallest subgroup, right? It is the smallest subgroup is the smallest subgroup of K containing S, right? And how do you know exactly that such a subgroup exists? You just simply take the intersection of all subgroups of K containing S, right? That intersection is also not vacuous, because K itself is a subgroup of itself containing S, right? So you take the intersections of all subgroups of K containing S, that subgroup that you get, indeed intersection of any family of subgroups is a subgroup. That subgroup that you get is actually the subgroup generated by S, right? So in other words, it is the smallest subgroup of K containing S. Okay, so we are only going to use this for our problem. So let's come to part A. So certainly we know that subgroup generated by A and AB, okay, so I mean to say subgroup generated by A and B contains A and B, right? And what is the smallest subgroup containing both A and B? Sorry, I'm being stupid here. Subgroup generated by A and B contains A and AB, right? Because A and B are there, so their product will also be there. So it contains both A and AB. And what is the smallest subgroup containing both A and AB? It's just the subgroup generated by A and AB. So the subgroup generated by A and AB is contained in the subgroup generated by A and B. We just need to show that the other inclusion also holds, right? So we just need to show that the subgroup generated by A and AB contains both A and B. Now, subgroup generated by A and AB contains A clearly and contains A inverse. Since A is there, its inverse will also be there, and since AB is there, so the product A inverse times AB will also be there. So this is B, right? So subgroup generated by A and AB contains both A and B. And what is the smallest subgroup containing both A and B? That's the subgroup generated by A and B. Thus, subgroup generated by A and B is also contained in subgroup generated by A and AB. So we have this, and hence the simple axiom of extensionality in set theory, that is equality of sets, basically says that subgroup generated by A and B is the same as subgroup generated by A and AB, and you are done. As simple as that. So let's also do problem, the second one. So subgroup generated by A and B has to be shown to be this. Okay, it can be correct or it might not be correct, but let's see. So again, subgroup generated by A and B contains all products of all powers of A and B, right? So in particular, it contains BA B square and BA B cube, right? And what is the smallest such subgroup containing these two elements? That is a subgroup generated by BA B square and BA B cube. So this is clearly contained in subgroup generated by A and B. So we just need to show the reverse inclusion, and that is again very trivial. Why? Because now subgroup joined by BAB square and BAB cube contains BAB cube it contains BAB square, which is an element, so that its inverse is also here, times BAP square B, right? That is BAB cube, right? Which is precisely equal to, so this is just BAB square inverse times BAB square B, right? Which is just B, right? So it contains B. Also, since it contains B, the subgroup joined by BAB square comma BAB cube contains, since B is there, its inverse is also there, you can multiply by that inverse. So it contains B inverse times BAB square times B to the power -1 whole square, that is B to the power -2, which is just A, right? And what is the smallest subgroup containing both A and B? Is the subgroup joined by A and B. Thus, subgroup joined by A and B is contained in subgroup joined by BAB square and BAB cube, right? Hence, you are done. Hence, subgroup joined by A and B is precisely equal to subgroup joined by BAB square and BAB cube. Okay, and that finishes this. So the correct answers are both A as well as B. Both of them are correct. Okay. So I'll solve this last problem. I'll write down the solution of this and I'll share this. Okay, so that you can see it. And that's all from my side. So do you have any questions? If you have, you can always ask me in the chat. Bhuvaneshwari, right? So do you have any questions? Excuse me. So you have been quiet the whole time, right? So if you have any questions, you can ask me. And if not, then we can end the discussion for today. So I hope you don't have any questions as such. So let's end the meeting or the session for today. And do, as I said, do attend Harish's session, which is supposed to be held every Friday. So he solves part of the assignment and I solve the rest of the assignment. Okay, so that is how it goes. So do attend those sessions and see you next week. Okay, so I'm ending the meeting. Let me just stop the recording.